Hi, my name is Gargee. I'm going to be a rising junior at Creighton University. This summer I had the opportunity to work with Dr. Dasbiswas in his laboratory where we investigated the motion of myosin as it moves into perpendicular stack formation as seen in fibroblast cells. So I'd like to start with some background information and hypothesis. So the cytoskeleton, which is found in eukaryotes, has many responsibilities. Many of them are structural responsibilities in the cell. So there are many components of the cytoskeleton. An important one is actin, which is a fiber which is able to grow and shrink through polymerization and depolarization. Another one is myosin. This is a molecular motor, and what it does is it provides a force which is necessary for movement in the cell. This picture that you see here showcases the inside of the cytoskeleton of a fibroblast cell. As you can see here, the actin has been labeled here in red, myosin found in green. And as you can see, labeled in the cartoon image, myosin is found in both filaments, which is a single myosin, as well as stacks, which is many myosin together. As you can see, it's found both along the actin, but also perpendicular, which is why we reference it as perpendicular stacking. So the question is, how does myosin produce this force? Well, myosin, as you can see in the cartoon image, is a double-headed motor, and it desires to walk towards the positive end of actin. When the heads walk towards the positive end of actin, they thereby slide actin filaments against each other in opposite directions. This produces a force which is necessary for movement. Now, the question that we want to investigate is, why do the myosin move into a particular perpendicular stack formation? We believe it's due to the structure of the actin network. As you can see in the cartoon image, the actin network is made out of parallel actin fibers. But there is also an intervening network of actin which connects these fibers. This network is able to pass along forces throughout the network and also respond to any force that gets acted upon it, because actin has a certain elasticity to it. So if it gets deformed at all, it wants to come back to its original conformation, and it does this by producing a force itself which can move things like myosin along it. So on a grander scale, we particularly are investigating non-muscle myosin 2. This is the lesser studied myosin compared to muscle myosin. In general, though, motors are very important for cellular movement. And as we all know, in order for cells to achieve many of their functions, they need to be able to move. Many of their important functions include motility, division, and muscle contraction. In particular, we are studying also the structure and formation of the myosin, because their structure affects their ability to produce a force, and thus ultimately their ability to move. On a grander scale, if this ability to move is impaired or irregular, it can lead to larger scale diseases such as cancer or heart disease. Thus, it's important to understand the mechanism behind their movement. Moving on to results. So we studied many similar images as this one. This is a cutout from that original larger image we saw provided to us by Xinqiang Hu and Alexander Brushatsky. So as you can see in this image, this is an actin fiber, and there's a lesser seen actin fiber along here with a myosin right here and a myosin there, and there are myosins found along that actin fiber. Over the course of the video, which I am unable to play right now, the myosin will move towards the other myosin on that actin fiber. So I have showed that through this series of frames, which are the same video but colored and labeled. So as you can see, I have labeled 3 different myosin. Over the course of the movie, these 2 myosin, which are on the same filament, move towards myosin on this filament, but they also move towards each other. We were able to use softwares through manual and automated tracking to find the relative position of myosin throughout all the different frames. So this is over the course of 15 minutes. And through that, we were able to extract a slope of about negative 0.1 microns per minute. So one of our initial conclusions was, we know the value for the walking of myosin. It's approximately 1 micron per minute. Through all of our research and calculations, we found a slope of about 1 micron for 10 plus minutes. Clearly, this tells us the mechanism through which myosin moves into this perpendicular stack formation cannot be through walking, and thus it must be a more complex mechanism. To continue, as I said earlier, the myosin are moving towards each other. Both myosin 2 and 3 move towards each other, as well as move towards myosin 1. This tells us that there's movement both in the horizontal and vertical direction. Both of these movements are essential to this ultimate perpendicular stack formation. In addition, we see that myosin 2 moves towards myosin 1, but so does myosin 3, despite the fact that it is farther away. This points to the existence of mechanical forces that exist between the myosin and that are able to communicate this force that brings myosin 3 towards myosin 1 as well. And these forces get passed along the actin network. To explain why we found such slow velocities, we believe it's due to the fact that actin, as I said earlier, is a fiber that's able to polymerize and depolymerize. Thus, in order for this myosin to translocate and move towards other myosin, it requires that the actin network the actin cytoskeleton has to remodel, and this is a time-consuming process. Thus, the speed that we found is far slower than if myosin had simply been walking. So in terms of future work, we want to look at videos such as this one, where the myosin are clearly far more dense. Thus, it doesn't make sense to do manual tracking. So we want to use machine learning through using automated tracking software such as Elastic to gain data through this type of video about the general flow and velocity of myosin. So we have started this work by taking a small cutout of the dense myosin and using machine learning to identify different myosin and track them over the course of a select number of frames. And this is a preliminary study, but more work has been done in the past week, so if you'd like to know more, please come visit me at my poster session from 12 to 12:50. These are my references and acknowledgements. Thank you so much for listening. I would like to thank CCBM, NSF, and UROC UC Merced for this wonderful opportunity to do research over summer. I'd also like to thank my faculty mentor, Dr. Dasbiswas, as well as Dr. Quint for all the support that they have lent me over the course of the 9 weeks. Thank you so much. Are there any questions?